I'll just give it another minute before we make a start. Okay, we'll make a start. Hello, my name is Darren Wolfe. I am the chair of the CIBSE Building Simulation Group. I also work at Worth Research and Loughborough University. Before we get into the awards themselves, I'd like to give you a brief summary of the activities within the Building Simulation Group over the last year. So this year we've been meeting quarterly as a virtual committee, and we've just had our 50th meeting since we've been founded just over 10 years ago. Our current activities include looking into how we can expand our network with like-minded groups inside and outside CIBSE, with more cross-promoting and co-presenting the simulation aspects within various events. You may have been following our certification initiative called CERT. This is initially intended to develop CPD-like training based on 3 chapters of our AM11 Building Performance Modelling publication, expanding to more chapters at a later date. We're looking to launch perhaps in the second quarter next year, so please sign up to our Building Simulation Group and watch out for more news on this. We've also started a new series of dynamic thermal modelling based publications coming under the banner of Best Practices Initiative. The first pilot publication is called Simple Blinds. We have 3 lead authors and a committee of 6 or 7 who meet for an hour every 2 weeks to guide the writing for the next 2 weeks and edit what's just been written. We're targeting a document about 10 pages long, which will demonstrate the significant variations you may get in heat gains and heat losses when you simulate blinds as a result of the different ways, the way different physics is captured in different models and different user applications. It will look at limitations in some of the common software packages and suggest some workarounds in order to get better representations within your calculations. Again, we're looking possibly to the second quarter next year, if not before this. Next year, we're also aiming to start looking at SBEM and see how the compliance methodology might be able to be improved. Finally, we're developing our 2050 future simulation vision so that we can map what we need to do within our group, developing our near to midterm activities. I think it's a really exciting time to be involved with building simulation, and we'll see many changes over the coming years. There are many drivers for change, such as technological advancements, net zero, climate change, and even a global pandemic. But it is ultimately us, the building simulation community, that needs to drive this change. We're always looking for people to provide support for our initiatives in what is a voluntary sector. So please email exec, that's EXEC, at cibsebsg.org if you'd like to get involved. I'd now like to pass the mic over to Darren Coppins, Building Simulation Group Vice Chair and Chair of the Judges, in order to take the Building Simulation Awards forward. Good luck to all the entries, and thank you.
Thank you, Darren. Great introduction there. So I'm just going to now introduce the 6 shortlisted candidates. The videos that will follow has been put together by them to essentially showcase what they've put forward. Me and myself and 2 other judges, Gabriella and Vasiliki, will be viewing these and actually asking questions and judging live today. and then we'll be going away and deliberating once those videos are complete. So if I can pass across to Alex to show those videos, please.
Hello everybody, I'm Alex. I'm the CIBSE BSG event secretary, and I'll start broadcasting all the entries. So we'll start with the first one, which is coming from France. So Adrien Domelat from Artelia and Energy is going to present the first shortlisted entry. Just bear with me for a second.
My name is Adrien Gimollard. I work at Energy in Paris. I will present you a self-deployed method to minimize simulation and analysis time. I will talk about a project I completed with my previous company, Artelia Sustainable Building. The project is a public French central city hospital, including more than 200,000 square meters, 5,000 thermal zones, 150 air handling units, and 13 buildings with energy plus simulation output files greater than 30 gigabytes. The heating and cooling system is a tempered single duct loop in green on the schema. It is used as source to make simultaneous heating and cooling at building level. At district level, the loop makes it possible to share heating and cooling energy. In its main operating mode, the loop heating and cooling is provided by geothermal wells. Thanks to the system, we anticipate a low consumption of 186 kilowatt-hours per meter squared per year, 3 times less than the existing one. This slide shows the project complexity. This is the design builder model, including the 50,000 square meter buildings and its HVAC system. For the project, we had to keep this accuracy level inside each building and then represent the loop with all buildings working together. This work had to be done in 6 weeks with 4 teammates. In a typical building simulation workflow, every engineer models a building and analyzes results on their own computer. This creates a lot of very large simulation files. If any human errors occurs, we need to correct, rerun, re-export, and reprocess files. In a normal workflow, the final Excel post-process file is finally useful only for the project. With the new method, we only correct, but the simulation and export time is highly reduced by BI tools. In this case, the modeling is done on the engineer's computer, like usual. The energy plus input files are generated from Design Builder. Then, thanks to the Design Builder's simulation manager, we can easily run simulation on one more powerful server to run faster. Then, a script automatically organizes data in a database, in this case PostgreSQL. When data is stored in a database, BI tools help the engineer to analyze, update, and aggregate the data much more quickly and easily. For this project, we were still forced to use Excel to make the final job, due to dynamic or stepped analysis. But the export is much easier with BI tools' help. On this slide, we see an extract of the Python script. On the left red frame line, we see a simulation detection. On the right, we see an extract of the shell script. The red frame lines show the table creation and indexation, while simulation is finished. My point here is to explain how simple aggregation is with a remote dataset. This example is the sum of all the aggregate cooling and heating rates of coils. The database is large, but we just query the servers to get the data we need. Thanks to the indexation power, it does not matter how large the result files are. The table view below can be exported in 2 simple columns for Excel, and if we need to analyze the results for more buildings, we only need to change the source and the result can be viewed automatically. Like I said, we use software available in most companies. Design Builders is used a lot in France, and Power BI is included in Microsoft Office licenses. This slide shows another view of the year's loop temperature analysis. The loop highlighted in green on the right depends on the well's position and the building's mode at time t. So thanks to the previous exports, we have the full cooling and heating demands of all buildings already stepped. After inputting the first temperature for the first hour in green, all the rest is calculated based on only warm and cold rejection on the loop. To conclude, the project was so huge and complex that we could not have estimated its energy consumption without this innovative method. This shortened our study time by at least 2 weeks. We did some corrections the last week. This could not have been possible without the server. Our study proved that it was possible to guarantee the tempered loop temperature, which was our client's condition to keep this highly efficient system. At last, the model was used to exchange with HVAC business unit to adjust and propose good regulation rules and have an appropriate sizing of every production component at building level and district level. So, this method saves significant time and provides an easier way for the design team to share and use the simulation data. Finally, I want to thank my teammates from my previous company, Artelia, and my new company, Energy. This was a really challenging project. Thank you.
Oh, thank you very much for that. I think Gabriella is going to ask a question for you.
Thanks, Adrian, for a great presentation. A very short amount of time to go through very complex type of work you've carried out. My question is regarding how you think this process can be replicated by others, and whether there were any other experts involved from other disciplines in this project.
So this is a good replicable. Sorry for my English. We use it today to analyze all our buildings, because it's an easy way to have pre-calculated views to see air handling units, for example, in Energy Plus, and have some data on it, maximum outdoor airflow rate, for example, and get the full information. It's easy to see, and we don't need to make a new process file. This is only for the database view, but we can also make parametric studies. This is the next step. And I'd like to use it for IPMVP parametric to make a lot of simulation. And with a friend, I will try to use RabbitMQ or QManager to install it on all the computers in the company to use at least 1 or 2 cores on each computer, and then have a full power to have so many simulation at the same time possible.
Thank you. It does seem like we're getting more and more involved into some data analytics and more involvement with IT into considering processing power for this type of analysis, right?
Sorry, I did not good understand the question.
No, I meant that from what you've shown us, it shows the need of more data analytics into building simulation, and that we need to integrate computer power into this, as you were mentioning.
Yes, exactly. Yeah.
Okay,
Thank you.
Thank you for that question and your answer, Adrian. I'd just like to ask a question as well, if I could. What stage of the project was the modelling undertaken at, and were your findings and proposals actually incorporated into the project at the end?
I'm sorry, it's too complicated question. I don't understand which stage of the project.
So, was it done at early design stage, feasibility stage?
No, in this case, this was the final design stage. This is for this reason and certification. French, like BRIM in England, we need to have as-built user. As will-built documentation, so with the full AHU data inside the building. So this was the final stage.
I see. And so your model reflected the building as constructed?
So the construction did not begin today. The hospital should be finished in 2026.
But it's incorporated everything that you've put within your model?
Yes, the rules, regulations rules should be integrated in the as-built documentation, and the simulation is part of the rules for the future company who will build the building.
Okay, that's fantastic. Thank you very much. Over to you, Alex.
Thank you very much for an interesting presentation. So we're now going to continue with the second one, which is from Meredith Davey from AD10.
Thank you for inviting Atelier 10 to talk about Jewel Changi Airport. The project is located in Changi Airport in Singapore and is fundamentally a retail destination. There's 100,000 square meters of retail and ancillary accommodation, plus a 20,000 square meter covered garden that is fully air conditioned. A key part of our work has been how we could deliver those spaces in an exceptionally challenging climate and an exceptionally challenging internal environment. We incorporated building physics analysis into the core of our workflow to be integrative and informative as to the development of design, rather than just validating whether the design works at the end or not. As part of this, there's a lot of work done looking at daylight access from skyvault views through to detailed mapping of daylight and cladding sensitivity on different areas internally, through to detailed evaluation of how the sun tracks through the space, and detailed evaluations of internal thermal comfort. However, there were two specific challenges to this project which required particular building physics analysis to resolve. We had the world's largest indoor waterfall, and we had a set of trains running through the building in a counterflow with two trains running each way every few minutes. The waterfall was a particular challenge as, quite simply, they had not been evaluated analytically in any great degree of detail before we undertook the work at Jewel Changi Airport. We had to evaluate how the droplets of the waterfall would create air motion, and we did this in two ways. We started with statistical analysis of looking at drag factors on individual water droplets and scaling that up. We looked at a top-down approach of dropping droplets in a CFD model to assess how those entrained air around them. And once we've converged those two approaches into a common understanding of the air motion, we then were able to merge that from a 2D model into a full building model. The initial results were not great. We were seeing very fast entrained air coming out of the waterfall, which was far faster than would be comfortable and would also dramatically de-stratify the space and render the displacement ventilation system and conditioning unworkable. Working with the architects, we looked at the airflows projected from the CFD models to then develop this quite delicate glass balustrade. As the air comes out of the vortex at the base, it entrains across the surface and is pulled towards the rest of the space. The balustrade just simply kicks it upwards vertically and creates its own air curtain from the air movement it introduces to itself. And this creates this kind of storm cell inside the vortex of this incredibly fast-moving air, but actually leaving the rest of the space very serene. We tested this through CFD and then validated it through limited physical mock-ups. But without this, the space would have fundamentally not worked. Alongside that, we had the challenge of the train. No one's really built a building with trains running through it on a regular basis while still trying to maintain quite close control conditions across the spaces. We had to look beyond our standard toolset to look at this and partnered with Siemens and CD Adapco to use some of their advanced clusters to model the effects of the train. We'd previously identified a need for fast-acting roller doors on the sides of the buildings, but due to the speed of the trains and the frequency, they were not able to fully close before the train passed through them in an airlock configuration. Using a dynamic CFD model, we were able to already assess how much air moved into the building and out of it, and found this very interesting effect that while the train comes through, some air gets dragged behind it. But the counterflow of the train coming out of the other way actually then helps to drag air back out of the building, meaning the net effect of the airflow is relatively minor and could be accommodated through local detailed design of the conditioning system near the throats of the trains entry into the building. We worked on the project from competition through to completion using analysis every step of the way. Through the construction on the site, we continue to validate and continue to work on the analysis, progressing its detail. to the completion of the project as more and more information became available, and making sure that those decisions that are made on the site were appropriate and responded to what the building needed to do. When it opened last year, we found this amazing space, the space that you just walk around and people smile, looking with joy at the building. Without the building physics on the project, we don't think we'd have had the same reaction, and we wouldn't have had nearly the same space. Thank you.
Thank you very much for your presentation. We've actually got a question now from Vasiliki. So if you could ask your question, please, Vasiliki.
Hello, I thought it was really great what you did with the CFD analysis, and I wouldn't expect a train to have so much impact in the airflows, but it's really interesting to see. My question was actually about potential integration with of the CFD analysis with the heat balance of the space and the energy balance of the space. So if you managed to integrate that in some way.
Yes, I mean, I really kind of barely scratched the surface of the work we did on that project. So there was a full energy model developed alongside this. We didn't directly link the two software tools because doing time-evolved CFD models on a project of this scale is just not easily feasible. But what we did use, the way we coupled the workflow was we were using the CFD model to inform the zoning and the way we were forming the dynamic model, the dynamic thermal model, so that we could make sure that we were capturing bulk air movement in an appropriate manner in that model, and vice versa. The initial configuration of the CFD models stemmed from boundary conditions coming from the dynamic thermal simulation. So it was an iterative process, but it was a human mediated one. I mean, it was frankly a very large CFD model that took several days to converge on a single time step. Hence why we were partnering with CD Adapco when we needed to do things that had dynamic geometry and rapidly moving load cases.
Mm-hmm. Yeah, okay, yeah, that makes sense. And computational time and power is again very important, like the previous presentation. Yeah. Thank you.
Thank you.
Great. Thank you both. I'll pass back now to Alex, please, if you could line up the next one for us.
Yeah, hello again. So the next one is Pushkin passive for Chapman VDSP.
Presentation is on the work my team and I did for the redevelopment of Manuel Island in Malta. The island is north of Valletta and around 146,000 square meters in size. The project comprises of residential blocks, marina, hotel, leisure and sports facilities. The climate is classified as a hot summer Mediterranean climate with 4 distinct seasons. Summer temperatures exceed 30 degrees when it can be quite hot and dry. The winter period is cooler but humid, and there is still a genuine need for heating. To prepare the sustainability brief for the master plan, we reviewed several international standards to identify sustainability measures appropriate for the project. From this, we developed a bespoke sustainability appraisal framework that included agendas that respond to the local context through an amalgamation of best practice measures identified from these standards. As part of the framework, we carried out extensive environmental design work, which I will go through now. We see building simulation as a method to refine a good design into an excellent one. To ensure solid design foundations, we prepared these 7 principles for early stage massing, which focused on orientation, arrangement of buildings, scale of courtyards, hierarchy in spaces, shading methods, materials, and creating an environmental transition experience. Moving on to optimization, we utilized several tools for our simulations. Bulk of the work was done using Ladybug and Honeybee. We used Xflow for running our CFDs and TAS for thermal modeling and validation work. Once the initial massing was formulated using the 7 principles, we carried out an early stage shadow analysis to quickly understand its impact on the outdoor spaces and the quality it created. The rapid feedback using this technique allowed us to tweak it before we started applying more advanced techniques. With the refined massing, we started assessing outdoor comfort using UTCI to identify areas of heat or cold stress. This was done for a typical summer and winter day in the morning, afternoon, and evening, when the spaces would most likely be in use. This helped identify the hot spots that needed additional shading features to enable comfortable outdoor spaces for the users. We used CFD analysis to check for overly windy conditions that would make the outdoor spaces unusable. Once the courtyards were defined, we did a detailed study of available sunlight hours to identify suitable spots for landscaping. For each location, we assessed the sunlight conditions to assist the botanist in selecting the most appropriate tree species. We also utilized the UTCI technique to create protected routes. Our design intent was to create a series of shaded and semi-shaded spaces for a gradual change in temperatures experienced by an occupant when moving from indoor to outdoor to prevent thermal shock. We modulated the massing to ensure there was a gradual thermal transition for the users. Since vegetation was integral to the courtyards, we also assessed the temperature benefit from the planting. This further helped fine-tune plant placement and pedestrian routes. And this render on the right illustrates how we were able to create different microclimatic environments in the courtyards. Moving on to internal design, we again identified key bioclimatic principles appropriate for the local climate, looking at external shading, natural ventilation, and thermal mass. There were two key design typologies that were identified by the architect for the design language. As part of the facade optimization process, we carried out over 2,450 unique simulations and produced a design matrix which captured combinations of orientation, exposure, and glazing proportion for the two typologies. With these results, we created a bespoke ranking algorithm to find viable solutions that create the ideal balance between thermal and visual comfort. Using a simple traffic light system, the design matrix helped the architect select the most appropriate facade option for different areas of the cluster. Once a preliminary option was selected, we carried out detailed analysis on the effective depth of horizontal and vertical projections to find the point of diminishing return of environmental value and energy performance. For a typical south facade, we achieved a 76% reduction of incident solar radiation and 62% reduction on the west facade. For all orientations, especially east and west with low-angle sun, we assessed different options for glazing and shading controls that will help reduce solar radiation whilst maintaining the sea views and privacy. We also interrogated the angle and spacing of fins as an external shading element, and as a result, we developed a movable screen on the facade which the occupant can slide across their windows when they want to block the sun whilst maintaining views and daylight. Towards the end of the design stage, we conducted robust validation checks using dynamic thermal modeling to confirm the performance was as predicted. This was done by testing for overheating risk and to check that we met our targeted potential hours for natural ventilation. For validating visual comfort, we used daylight autonomy as a metric to assess the quality of natural light in the space. Lastly, we carried out an iterative site-wide energy assessment to demonstrate the overall reduction in energy demand by the optimization process. As a result, we achieved a site-wide 40% reduction in energy demand just by passive measures alone. Thank you.
Thank you very much, Pushkin. That was a lot of information there in a very short amount of time, so well done. Very good presentation. Gabriella is going to ask you a question.
Thanks, Pushkin. Yeah, just second what Darren said. It's a lot to go through in a very short time. So for that, I would like to take the opportunity to ask you if you could expand upon this ranking algorithm you mentioned a bit more in depth.
Right. So essentially what we were looking at, the primary metrics we were looking at was comfort. So we wanted to, comfort was a key indicator that was part of the design process. So from the comfort perspective, we were looking at thermal and visual comfort. From the thermal comfort side of things, we essentially looked at two key methods. So obviously we have the 15251, the ISO 15251, as well as the CIBSE Guide A, the temperature ranges. And the other thing we were looking at was the potential of natural ventilation, the how many hours. So these are fully air-conditioned luxury apartments, but however, we still wanted to make sure that we maximize the the number of hours the occupants could naturally ventilate, and therefore have conditions that were comfortable without using active systems. So we developed criteria using these two methodologies of calculating overheating risk and comfort to identify what we call as recommended conditions or exemplar conditions. And similarly for daylighting and visual comfort, we looked at daylight autonomy as a metric, predominantly because for clear skies and hot and and sunny locations, daylight autonomy is probably a better metric to look at from the daylight perspective. And again, we had specific criteria called for recommended and exemplar conditions, where we say that I think 55%, if you achieve 55% of daylight autonomy, that's a recommended, and 75% or more is an exemplar condition. So a combination of these two factors together allowed us to build that algorithm to kind of attach to each of those simulations that we ran. And that's how we built this fairly simple looking design matrix for the architect. The intention is that we don't want to create thousands of different options for the architect to get confused. We want to keep it simple so that they can easily pick and select what they feel is the most appropriate for their design. I mean, in the end, it's the architects who are creating those sentences. We're just giving them the alphabet.
Thank you. Understood. So it's taking the standards and the guidance of the threshold and the criteria that there are and putting them into rules to help you guide the decision making.
Right. Yes.
In summary. Okay. Thank you very much.
That's great. Thank you. Alex, if you could line up the next one, please.
Yes, of course. So the next one is from Sain Orm from WSP.
All right, good afternoon, everyone. I'm here to talk to you today about a project that I was involved with about this time last year, in which we were helping support the architect in developing their bid to design the world's tallest tower. One of the main design features that we experienced over the project was the actual height of the building. So you can see here, in relation to some of the other world's tallest buildings, notably the Burj Khalifa at 830 meters, the Jeddah Tower at 1,000 meters, and our building, which over the course of the design project varied between 1 kilometer and almost 2 kilometers. The other major challenge was the arid desert design conditions. This had a summer peak temperature of 46 degrees and a winter temperature around 5 degrees. But keen mountaineers among you will know all about the dry adiabatic lapse rate, which basically means that as every 100 meters you climb, the temperature drops by about 1 degree every 100 meters. So this meant at the top of the tower had drastically different design conditions from the base of the tower, which was about 15 degrees cooler in the summer, but also at risk of freezing for large parts of the winter. So we had this constantly changing concept design, a very aggressive 3-month project timeline, and as well as very challenging environmental conditions. We got given information from the architect in the form of a building height, a building width, and typical floor plates. So I thought this would be a perfect opportunity to develop a parametric model using Grasshopper and Honeybee and Ladybug modeling suite. So using this, we were able to approximate the building geometry and assign thermal zones and set MEP assumptions for each of the building zones. We were able to write a piece of code to modify the weather file so that the environmental conditions were different for each floor of the building. So we were able to simulate each floor and then iterate this simulation up the entire length of the building in order to come up with the total building heating and cooling loads, as well as run daylight factor simulations, and a radiation massing study. So overall, we were able to receive design information and generate a series of design information, so run a series of sensitivity analyses, including a surface radiation study, daylight factor analysis, and concept energy analysis. And we were then able to feed this information back to the architect in order to inform the design decisions in a kind of iterative process. The first thing we did was an initial radiation massing study where we looked at different forms of the building. So we on this found that kind of triangular or tripodic building form had better kind of overall radiation versus a kind of more traditional square shape or triangle or a circular shape. We also ran a daylight factor and cooling load analysis. This highlighted the very deepest office floor plates. It had very little access to natural light. So these one strategy proposed by the architect was to introduce these kind of slots of the building, which had the combined effect of increasing the daylight factor and access to natural light, while also not impacting the cooling load significantly. So we've been developing this model for about a year since then. We've added a few extra features. So in addition to running sensitivity analyses, we are able to run optimization studies of these different design decisions based on a genetic evolutionary algorithm. And we've also extended the capability of the model to start looking at some more detailed design decisions. Some of them there on the side there. Right, I think that's about all I've got time for today, but just like to thank everyone for listening and happily answer any questions. Thanks.
Very good presentation. Thank you very much, Shane. I've got two questions actually. The first was I'm quite interested to know a little bit more about the code in terms of altering the weather file and then how you simulate that to apply across the height of the building. And the second one was whether you considered any beneficial gains and losses associated with where you are in the building and the height of the building and how energy could potentially be shared.
Yeah, so yeah, that's a good question. So the basically how the simulation worked was that it basically did a typical floor of the building. So it calculated each floor of the building separately and then kind of iterated that process as you kind of climbed the building. So it repeated that on each floor. So the geometry would change as you shifted up the building. We also had a kind of program schedule from the architect because it was massively mixed use building. So we had, offices, 5-star hotel, residential buildings, lobby areas, which all had different kind of MEP input assumptions, so different loads and things like that. So yes, and then in terms of changing the weather file, so we simply we applied basically the kind of psychrometric principles of the so as you increase in altitude, the pressure reduces and the gap in the atmosphere expands, so it gets a lot colder as you increase the building, and there's kind of equations that I won't go into now, but you can apply to the weather file to change the humidity and the temperature and so on. So we basically did that at each step as we moved up the building. And yeah, that was one of the kind of main challenges of the project. So obviously the building that high, pumping water up to that height is a real challenge. But due to the kind of dry, arid conditions, cooling towers are probably the best method of meeting that cooling load. But there's a kind of crossover point as you move up the building, which we had where cooling loads become the less good as a result of the pumping energy, and you could move to a more to a kind of air-cooled system, and we found that height to be about 600 meters. But yeah, I hope that answers your question.
No, that's very good. Very interesting building. Got loads more questions, but we'll have to wait for those for another day.
No worries.
Thank you very much, Shane. Alex, could you line up the next one, please?
Yes, so the next one is Simona Vassington from Cantal.
Good afternoon, I'm Simona Vassington and I'm a senior engineer in the Candle sustainability team. Today I will be presenting how we have optimized overheating assessment for residential and commercial buildings using Python in IS. As we all know, we are in a climate emergency and the UK is committed to achieve net zero carbon by 2050. To meet the 2050 target, it has become essential for the building industry to deliver future-proofed buildings while also minimizing carbon emissions in operations and ensuring occupants' thermal comfort. As per Candle's 7 steps to net zero, passive design optimization is the first and arguably the most important step in creating net zero buildings. Several design features have to be investigated at the early stage through the lens of energy use, daylighting, and thermal comfort, as well as resilience under future climate scenarios. To achieve this level of detailed design at early stage, we have been developing tools to automate and optimize design workflows, from energy calculations to daylighting and thermal comfort assessments. With the following objectives in mind: to be able to deliver in a short time an in-depth analysis of several design parameters, and to reduce time spent in tasks that don't have any engineering value and increase time spent in analyzing the results and their impact on the design. When assessing thermal comfort, to validate the efficacy of a design, 3 main methodologies are used in the UK, and these are CIBSE TM52 for commercial buildings, CIBSE TM59 for residential buildings, and BB 101 for primary and secondary schools. IS is one of the software most used in the UK industry to carry out these assessments. Within IS, it's possible to produce an Excel report for TM52, but not for TM59 or BB 101 methodology. To calculate this, as well as the impact of different internal airspeeds, additional calculations have to be carried out in Excel, which is an extremely time-consuming task. Luckily, there is a Python environment within IS that allows the development of customized scripts. What I did was to develop a script to optimize how we carry out these assessments. The first objective was to embed all calculations for each assessment within the script, to be able to run multiple weather files, to embed calculations for several internal airspeeds, to output the results in a user-friendly format, such as Excel, and to develop a script that can be used by any IS user without any Python knowledge. This is a graphic representation of the developed workflow using Python. The first step is to set up the model in IS and to fill in an Excel with the simulation inputs, such as the weather file and airspeeds to be modeled. The second step is to open the Python environment within IS and run the script, which will run all the simulations with all the weather files in the Excel input spreadsheet and the airspeeds. The results will be returned in Excel in a table format within the project folder, and then at this point they're ready to be analyzed with any data analysis tool such as Excel itself, Jupyter, or Power BI, depending on the user's preference. The use of this workflow guarantees quality of the calculations compared to post-processing calculations in Excel, an output which is easily readable by any data analysis tool, an in-depth analysis delivered in a short time, transferability and repeatability of the workflow on the same project and across several projects, better use of the engineer's time, and the possibility to integrate additional features within the script, such as calculations that go beyond the methodology requirement. This graph shows a comparison between a traditional workflow, which is IS and Excel, and the developed workflow, IS and Python. On the y-axis, we have the time, and on the x-axis, we have the number of iterations. Assuming we have to start from scratch in both cases, writing the Python script requires a longer development time compared to setting up the same calculations in Excel. However, as the number of iterations increases, in the Python workflow, the time required to complete the same task is a small fraction of the time required to carry out that task using IES and Excel. And as the number of parameters to be analyzed increases, the gap between the two workflows is even bigger. This shows how the use of the developed script highly increases efficiency in delivering these tasks, making best use of the engineer's time. This workflow has been used on several projects for residential, schools, or commercial buildings. Among these, a number of net zero school projects we have been working on in the last months, where the analysis of several parameters and climate scenarios for different locations in the UK was required at concept stage. The use of this workflow across projects shows one of its strengths, which is transferability and repeatability, as well as the capacity of delivering in-depth analysis in a short time. Any question?
Thank you very much for your presentation. Another very interesting, very good presentation. I'm going to pass across to Gabriella to ask a question.
Hi, Simona. Thanks for the presentation. As we all know, it's very useful to optimize the steps in any of the software tools that we use. Going through the presentation, something came to my mind that I was thinking, how could this approach of scripting could help you reflect changes to the design quickly, which seems to be what overheating assessments are more and more based on, evolving changes in the design. So how do you see the work you've done to helping you also minimize the amount of time you spend remodeling for overheating analysis?
Yeah, I mean, the use of the script usually, I mean, we have used it on several projects, so we have actually tested it. And what you do is like you define your design parameters and what you want to analyze and which design, the impact of each design parameters. And what you do is then just like the fact that you're using the script and you have the capacity of running multiple weather files and multiple airspeeds. Once you have set up your model with as many parameters as you need to analyze, it's quite easy to run all the simulations using the script, and I just have your output in Excel with it doesn't matter the size of the output because it's not something that you're going to do manually. So the post-processing is done by the script, and that allows you to model as many parameters as you want and then just focus on the analysis of the results. So there is no, you can implement and integrate in the initial model as many parameters as you want to test. And that's then can be transferred in the design, that you can just discuss that through design meetings with the client and make decisions at the early stage. I think that's the most important aspect of being able to analyze that many things in a quick time. So being able to discuss this at the early stage and actually integrate important solutions within the design.
Thanks. Vasilika has a follow-up question, if you have a couple of minutes.
Hello, thank you, Simona, for your presentation. Yeah, well, my question was a follow-up to the presentation and selection of design strategies and the potential to integrate a visual aspect to the simulation workflow. So how to present the results visually?
Well, most of the time, like since your output is in Excel, what we have done, it depends on the size of the project. So that's the advantage of the script. It depends on the size of what you're modeling. It can be a few flats. It can be closer to a research project for net zero school. So you have thousands of spaces that you're analyzing with different parameters. So the output is always in Excel, which is a format that can be easily used and understood by any engineer. So depending on the user's experience of who's analyzing the results, we have done it in different ways depending on the project. So we have presented the results with the interactive dashboards in Power BI. We have presented the results in simpler tables in Excel, or we have analyzed the results using Jupyter and Python again. But it depends again on the format of the output and the size of the data set that you get from the simulation. So in other cases, when the size of the data set was quite big, we have analyzed them using Jupyter. And from there, you can just pull out graphs that show the conclusions of your analysis. So yeah, I think that's one of the advantages of the workflow, that since the output in Excel, then depending on the size of the data set and the experience of the engineers, it can be analyzed in different ways, and the results can be presented in multiple ways.
Great, thank you.
Great. Thank you very much, Simona, Vasiliki, and Gabriella. We are running a little bit behind, so Alex, if you could line up the last one, please.
Yes, so the last one is from Joseph Pettit from Hilsham.
Hello, I'd like to present our entry for this year's CIBSE BSG Awards. I'll tell you a little bit about our Healthy Cities tool and show how we used it when developing a master plan in South Korea, and hopefully show how it helped us to overcome some quite challenging conditions. The Healthy Cities tool, it uses Rhino and Grasshopper to drive simulations of various environmental assessments like thermal comfort and acoustics and air quality. And it drives these assessments inside the Rhino environment. Well, the Healthy Cities tool, it started out just as a tool for conducting thermal comfort assessments. You know, we've been doing CFD wind simulations and combining them with radiation analysis and building dynamic thermal models for years now. But on the general principle that if you do the same thing more than a few times, then you should really think about automating it. So we used Rhino and Grasshopper, not just to coordinate the geometry, but to run the simulations directly within the Rhino environment. Then over the last couple of years, we've, having established a decent platform, we've started bringing in other environmental assessments like acoustics and air quality. And you'll see in a minute how South Korea made good use of those. And also the ability to very quickly compare designs with a design comparison, design explorer. So in Korea, it's at the eastern end of the Asian continent, so it's got a very continental climate, very hot summers, very cold winters, so challenging thermal conditions. Also, there's a lot of pollution coming not only from Chinese industry, but also a lot of dust coming off from the deserts over there. And also in the Korean cities, there's a fair amount of traffic issues, and that affects the not only the pollution, but also the acoustics as well. So here's a brief overview of the master plan that we were working on, and in particular to the northern, to the top end of that image. There's a plaza area in amongst the pink blocks, and it's a bit difficult to really show how we drive the models from within Rhino, but you know, not in a presentation like this, but you'll just have to take it from me that these results aren't images that are just within the Rhino model. They're actually being driven and produced within the Rhino environment. There's that was wind, and now this is pollution, PM10 and PM2.5 results. You can see it's a very coarse, very high level assessment. That's the acoustic assessment. And you can see how it can be used to show the various different highlights in a given location to help a client or an architect understand. The other thing we've done on this project is to do a parametric assessment using the local climate data to look at how the streets should line up with their orientation with around the compass, but also whether the highest building should be in the middle or at the outside edge, and whether the city street grid should be shifted maybe. And we can discuss the various pros and cons of these things with the architects, with the clients and the stakeholders, particularly by using the Design Explorer that I mentioned. This one's looking at various levels of comfort, thermal comfort, but it can also apply to maybe getting a balance between thermal comfort and acoustics, where these are sometimes competing metrics. And then finally, I'll take you through the overall nature of the design process that we went through. So this is how the conditions would be felt if the city blocks were just straightforward extruded blocks to all the same height. You can see that in the summer it feels like 38 Celsius, and in the winter it feels like -22. So very challenging conditions. But by optimizing the overall shape of the master plan, making it higher in the middle and lower at the end so that the wind flows over the top, by deflecting the wind that is steered down the canyons, this is all about optimizing conditions in the plaza space, by blocking off those canyons at a higher level, and also by adding just a little bit of solar shading, and this also helps the aerodynamics of the buildings. You can see that we're able to add a fourth thing in addition to the optimized deflect and protect. We're able to also take some of the air from the buildings and blow it into the plaza area to slightly pressurize the space. And because of all the shielding that's going on, the conditions within the space are shown to be, in the summer, we've got it down to about 25 Celsius, and in the winter we've got it up to about 0 Celsius. And the client was extremely happy with these indications. And just very quickly, I know I'm a little over time. Some of the things that we're working on to improve the Healthy Cities tools, improve the quality of both the air quality and the thermal mass, improve the accuracy of the modelling there. And also we'd like to, the acoustics at the moment still has a little bit of human intervention, but we're hoping to bring that to a close. Thanks very much.
Thank you very much for that presentation. Again, a lot of information there in quite a short period of time, Joseph. What I'd quite like to ask about is the acoustic aspect. Acoustics and acoustic modelling is something we don't do enough of, I believe. So could you tell us just a little bit more about that in terms of how you modelled it and what the key variables were?
Well, the work we're doing, it's all very, very early stage that this work is done on. And the acoustic modelling is mostly done with CADNA, and the models are generally set up through the Rhino. And there's still a bit of work, as I said at the end, we're trying to bring that inside the Rhino environment. There's still a bit of human intervention that's needed. But the models are very simple. Just to give an indication of the impact of the traffic, we're doing some impacts of softening walls, that kind of thing, and porous screens. It's not very detailed, the acoustic work. It's one of those things where with this platform, we're starting to keep things very simple and then grow them from there incrementally rather than put a great deal of detail in at once.
Okay, that's fantastic. Thank you very much, Joseph. So I think now myself, Vasiliki and Gabriella need to go away and have a little bit of a debate. So whilst we're doing that, I'd like to introduce our chairman, Darren. And Darren is going to essentially chair our panel debate, and we have some videos as well from our sponsors. And the debate is on the future of building simulation. Darren, are you there?
Thank you, Darren. So before I invite our sponsors who form our panel for the debate, as Darren said, we'll be having a number of videos, short presentations that they have put together. And what we did was we set them a task to think about the major trends in building simulation, and gave them a 5 to 10 year framing. And I'd now like to ask Alex to start the first of those videos.
Yes, so the first one will be from David Kokin of Design Builder.
Hi, I'm Dave Cocking from Design Builder. These are the 4 main trends we've noticed in recent years. I'll now discuss each trend and explain what we intend to do about it in the short to medium term. Interoperability is the biggest issue facing many design firms these days, especially when running dynamic simulation, daylighting and CFD simulations via different tools. Sharing model data via GBXML, IFC, etc. can be problematic, regardless of the tools you use, often requiring models to be rebuilt in each software, and that consumes vast amounts of time. You can improve interoperability in two ways. Firstly, by one interface interoperating with all the calculation engines a modeler requires, using one model for certification, energy, comfort, daylighting and CFD simulations. That's been the approach used by Design Builder. But advances in technology and changing design practices are pushing this approach to its limits. I'll use examples including CFD, optimization and scripting to explain why. Design Builder's current CFD engine can meet most common building-related CFD needs, but it can't model particulate flows or pathogen dispersal and containment measures. The pandemic has increased the importance of these aspects. To help us meet these and other requirements, we'll soon be providing a user interface for the well-respected OpenFOAM CFD engine. So from one Design Builder model, you'll be able to generate OpenFOAM results and input and output files, alongside the Energy Plus and Radiance results and files already available, including your Energy Plus results as CFD boundary conditions. That should minimise the need for data transfer between different simulation tools. However, many firms will still want to use multiple tools in their workflow. This slide shows a past project workflow using this kind of multi-tool approach. The Design Builder model was exported via Rhino to Grasshopper and Ladybug to optimise the PV array tilt angle and spacing, and then imported back into Design Builder. The tools used in this workflow can import files from open source engines such as Energy Plus, making interoperability easier via interfaces to those engines. We're now actively developing software to improve data transfer between tools, including via an API we released recently. The API allows users to develop their own applications to interoperate with Design Builder. The API and wider interoperability capabilities will be enhanced in the months and years ahead. The increasing complexity of building HVAC and control systems has increased the need to customize some simulations, normally via scripting. In its basic form, scripting allows the user to pre- or post-process simulation data, for example, to produce specific output reports. A much more powerful application is to use your script to modify the model behavior at each time step during a simulation. So, for example, you could replace the simulation engine code with the manufacturer or design team's control logic to ensure the simulation matches real-life equipment operation. Design Builder has provided this kind of runtime scripting capability for a while now, but given the strong increase in scripting interest, we're progressively extending this to include Python and C# scripting too. Optimization is a form of advanced cost-benefit analysis. You set the objectives for the analysis, for example, to minimize energy consumption, carbon emissions, or construction cost. The range of design variables that you select, such as different types of insulation, glazing, shading, HVAC, etc., are then auto-simulated in different combinations using a genetic algorithm to find the best combination of your design variables according to the objectives you set. Once the optimization is complete, the solutions that best meet your design objectives are displayed along the Pareto front of the results cloud, denoted by the red points you see along the leading edge. Optimization is a capability enhanced by the availability of cloud computing. You set up the optimization model on your local machine and then run the simulations much more quickly on a network or cloud server with multi-core processors running simulations in parallel. We'll be extending cloud computing beyond Energy Plus simulations in the years ahead. Last but not least is existing building calibration. Calibration develops a design stage model so it reflects operational reality, helping building managers to optimise operational performance, including energy efficiency and occupant comfort. Model calibration typically involves iterative fine-tuning using operational data from the building to create schedules that calibrate the model to reality. We're developing a toolkit to speed up and largely automate the calibration process. Much of the advanced functionality necessary for that is already available in Design Builder. For example, the uncertainty and sensitivity analysis and our optimization tools. Some of the additional components, including climate analytics tools for creating location-specific recent weather files, and additional results viewer functionality will be available early next year, with the remaining tools following over the next year or so. Calibration was discussed in the recent TM69 operational modelling webinar we did with CIBSE, and the recording is still available from both the CIBSE and Design Builder websites. Hopefully you found this glimpse into the near-term future interesting, and it's given you food for thought going forward.
So the next one, we're going to hear the response to this question from Andrew Hilmy from EDSL.
What are the major trends you are seeing in building simulation, and what are you doing in the next 5 to 10 years to respond to these demands? The current emphasis for future buildings, and therefore what we need to simulate, seems to be highly focused on people and the environment. People need an enjoyable place to work that enables collaboration and enhances productivity, and this is extremely important and valuable to a business because people costs tend to be around an order of magnitude higher than building operation costs. So even small changes in productivity can have a huge impact. Also, in light of the environmental crisis we're facing, we need our buildings to be carbon neutral at the very least. Buildings contribute around 28% of all global CO2 emissions, and because the stakes are so high, it really is so important that we can accurately predict the real energy consumption of a building before we actually build it and it's too costly to change. We're getting to the stage where relative comparisons between buildings just aren't good enough anymore. One of the big technologies that's taking all industries by storm at the moment is machine learning. So machine learning finds and applies patterns in data, which, in the case of buildings, we obtain via embedded Internet of Things devices. So these devices will gather endless information such as occupancy patterns, external weather, which lights are on, what the blind positions are, what people might be wearing, and use this information to intelligently predict good thermostat set points. Users could give feedback about their perception of the environment via a smartphone app that feeds directly into these machine learning models that control the building management systems. In terms of building design, we need to be able to simulate the operation of these machine learning models. We can also use machine learning to speed up simulation times and even help people create their digital models faster. Another area that's gaining interest concerns modeling occupant behavior. Currently, we tend to model occupancy and equipment gains as static, but in reality, it tends to be much more stochastic. Occupants tend to enjoy their environment more if they can interact with it by adjusting lights, thermostats, blinds, and windows. And they also affect the small power consumption. And uncertainty from occupants is very costly. So one study demonstrated that sizing a PV array to be 99.9% certain of net zero energy costs 50% more than one that is 90% certain. It's therefore very important that simulating occupant behavior leads to robust design. We need to make it very difficult for users to make inappropriate decisions. You may have seen the smart glass used in toilets in Tokyo. The same technology is very useful in buildings, particularly if the solar transmittance can be controlled independently to the light transmittance. We could have facades that allow the sun to provide more heat in the winter and reject it in the summer based on weather forecast predictions. And again, the control of these systems is something we'll need to be able to model in order to be able to refine the design. There are also continuous advances in energy storage technologies. take batteries, for example. Different batteries have distinctly different characteristics. If the population shifts to primarily electric vehicles, we may be able to use the car batteries in the building's parking area to smooth out peaks in the energy demand where renewables are relied upon. But we'll need to make sure that we give the employees enough power to drive home with. There is also renewed interest in phase change materials, thermally activated building systems, and HVAC UV sterilizers. If we can find a way to cycle UV sterilizers based on a model of pollutants, we could save a significant amount of energy. As usual, raw computing power continues to increase, and with that comes opportunities. Wind pressure coefficients and openable proportions tend to be a big source of uncertainty in natural ventilation calculations. We can more accurately estimate these using modern fast CFD for both exterior and interior modelling. We can start modelling CO2 factors that vary throughout the year. We can implement algorithms that generate future weather data from arbitrary weather data, such as data gathered by on-site weather stations. We can attempt more ambitious optimization and parametric design projects, though we'll need to spend some time thinking about how to present the vast amounts of output data to our users, because sometimes a lot of data can be a bit overwhelming. And we can combine a number of techniques and technologies to provide real-time results while we're actually creating our geometry, such as daylight calculations. Accurate glare analysis is particularly important if we're modelling occupant behaviour, as occupants tend to put the blinds down and leave them down, even when the risk of glare diminishes, so it's important that we avoid glare in the first place. And we can increase the temporal resolution of our simulations in order to capture some of the more intricate interactions between buildings and their occupants. Last but not least, one very significant opportunity lies in calibrated energy models of existing buildings. If we're going to reach our low carbon goals, existing buildings will need aggressive renovations, but sometimes it's hard to justify significant changes to envelopes and HVAC systems when the initial costs are very high. By creating digital twins of buildings, we can accurately predict the effect of renovations and calculate relatively accurate payback times. We can also quantify how much has actually been saved after undertaking renovations and connect this model to their building management systems to take the improvements and monitoring further. I know I've covered quite a lot at a high level and have been quite ambitious about what I think is possible in the next 10 years, but I think we're going to have to be in order to have a real impact on climate change. After all, buildings are quite long-lived. I'll make these references available somewhere in case you want to look into anything I've talked about in more depth, and I look forward to your questions.
So the next video is from Eric Roberts of IS.
Seeing in building simulation, and what are you doing in the next 5 to 10 years to respond to these demands? Hi, I'm Eric Roberts. In the next few minutes, I'm going to try and answer this question. I think before we do that, I think we need to look at where we have been and where we are currently, and then look at determine where we are going. So where have we been? So we've been on a process of digitization and moving away from a very paper-rich environment where many thousand people involved in trying to coordinate designs between many different disciplines. Obviously, with the advent of digital technology, this has made that easier, and with greater computing power, greater storage, we've been able to deliver more complex projects, as well as with interconnectivity and the internet growing rapidly, especially within the last 20 years, we've been able to connect all these dots together and bring people together, not just within companies, but across countries and continents. So you'd think this has helped us within the construction industry deliver great digitization of our products. As you'll see from this survey, construction industry only ranks one place above the agriculture and hunting in its actual implementation and how digital technology and how advanced we are as an industry in the digital realm. Compare this to some of the other industries that are available. People like aeronautics, etc., have been using digital energy for many decades in their products and throughout the life cycle of those products. When you consider that Boeing actually delivered its first fully digitally designed plane, the Boeing 777, in the 1990s, it shows how far actually we are behind as as an industry compared to these others. So where are we going to be going? How can we do that? So whilst we've come a long way in the last 20 years of coming from a paper environment through into a digital, hopefully a 3D environment, but not in all cases, where are we actually going to go? So we've brought the use of building simulation from quite a niche activity, although somebody may argue it's still a niche activity within within the construction industry. We've been looking at one building at a time. Predominantly, its growth has been compliance and regulatory driven directives to make this implementation in place. So it'd be more of a carrot, more of a stick rather than a carrot for people to do that. You know, energy has been cheap. Energy is still relatively cheap, and it's not, developers aren't the end users of buildings they're selling assets on. They're not bothered about the long-term running costs. As we move into a realm where we're looking at decarbonisation and low and zero energy buildings, we need to be starting to look at a wider and longer term time frame than this. So we need to look at going from one building at a time to looking at multiple buildings at a time, looking at cities, how they're interconnected. We need to look at the construction of those buildings, but we also need to look at the systems within those buildings, making greater use of HVAC modelling. A lot of people think it's a fairly new activity. It's something that's been around for many decades, but we're actually now only starting to catch up as an industry of bringing that in. But we also need to start sources of wastewater, power, potable water. Potable, very important. Without water, we have nothing. So we need to look at these resources, bring them together, analyse how we're using them, where best to use them, how to store them. And moving forward, starting to be talking about operational energy, looking at the life cycle of buildings, of starting to bring in digital twinning technology within those buildings, so actually looking at physical assets, knowing how a physical asset operates, having detailed models of those to know that the building is operating within its parameters, that it's all operating correctly at its optimum level, and how we can improve that. What are we doing at IES to implement this? Obviously, over the last number of years, we've been implementing a number of technologies for data gathering, for fusing that together with simulation models, developing tools to actually look at these resource networks and modelling multiple buildings at a time to be able to do that. Obviously, we're working towards improving that technology, expanding it, moving it towards cloud-based computing, greater access to these technologies worldwide, to our user base, and allowing people to carry out more detailed and quicker models and simulations than we have been able to previously. So I think that's where we've been, that's where we are currently, and this is where we're looking to go in the future. So for myself, thank you very much.
So the next one is from Nagman Khan from SimScale.
CIBSE Building Simulation Awards and the interim session on the future of simulation. My name is Dr. Nagman Khan from SimScale, and I'd like to quickly give you an overview of some of the trends and key issues we're seeing in the world of building simulation. First of all, SimScale is a German software company headquartered in Munich, and we have people all over the world. I myself am based here in the UK, and we have created the world's first cloud-based engineering simulation platform that specializes in CFD, FEA, and thermal simulation. We have hundreds of thousands of users worldwide, and SimScale is on the cloud. Now, what does that mean? It means that SimScale can be accessed via a web browser. So a simple username and login will get you access to incredibly powerful CFD and other tools, which makes it incredibly accessible and democratic and easy to use. Now, let me take a step back. What is computational fluid dynamics? In simple terms, it's engineering simulation used to model the detailed behavior of fluids. Now, in architecture, engineering, and construction, we can use CFD to model various things. For example, the wind, urban microclimate, natural ventilation, HVAC, and thermal comfort. And with SimScale, you can access CFD on a web browser using GPU-accelerated cloud simulation. We have several new generation of solvers, including the lattice Boltzmann method, which increase by an order of magnitude the time taken to simulate, real-world problems. So this, you can see on the screen, you're modeling a transient wind, which is a real wind. Ordinarily, a simulation like this on a large model in legacy desktop tools might take days to do. With SimScale, you can do it in hours. So it's an order of magnitude improvement. Some of the types of simulation we can do, for example, external simulation, you might use it for looking at building aerodynamics, pedestrian wind comfort and safety, wind loading, and a closer look at wind pressure coefficients. And you can do that, from the very early concept massing stage through to design and planning level quality. Indoor simulation focuses on things like understanding the flow of air in and around a space, looking at airflow diffuser types in more detail, and modeling different types of equipment, such as underfloor heating, and also looking at thermal comfort. So this is all entirely possible right now. The question is, what are the major trends we're seeing in building simulation over the next few years, and what is our response? Well, the first major trend is something called co-simulation. So we're applying the physics in CFD to complement thermal modeling tools. This is really important. And the reason is because a lot of these thermal modeling tools were developed 20 plus years ago when we didn't have the cloud, we didn't have the fantastic processing computational power we have now. So a lot of the physics in there was based on simplified relationships based on empirical modeling. We don't need to do that anymore. We don't need to shy away from that. We have tons of computing power available. So let's capture more of the physics, model the physics more explicitly, and let's bring this capability into the thermal modeling tools. We have some great examples where we've modeled the CFD generated wind pressure coefficients in SimScale and imported them into thermal modeling tools to make the accuracy of the dynamic simulation much better and higher. That's just one example. The other trend we're seeing is, look, we have one world, why not have one model? Typically, we simulate the external environment separately and the indoor environment separately. What we want to do is couple these more effectively, right? An example, the wind atmospheric changes, they have a huge impact on the heating and cooling loads and ventilation. So the question is, what kind of solver do we need to be able to capture this and couple that environment? SimScale have the next generation solvers, including the lattice Boltzmann method, that coupled with putting it on the cloud, using GPUs and really leveraging the parallel simulation capabilities makes this kind of simulation a lot more possible now and realistic. My final point is integration collaboration is very important. The typical design workflow is very sequential. Right, you'll have one kind of analyst simulation person, different people sending him or her requests to do types of analysis on a desktop CA tool. Really what we need to do is turn that around completely and give everyone or a lot more people access to different apps. So, you might have a wind comfort app, wind loading app, and architects, engineers, they can all access this, dip into it, dip out whenever they want to. And this is automated using an API, and it's hosted on SimScale Workbench. So, and you can involve all the different stakeholders in there. So the three key points: co-simulation, capture more physics, integration, and automation. Thank you.
So the very last response to that question is from Nick Hopper from Monodraft.
My name's Nick Hopper, and I'm the Technical Director for Monodraft. I've worked for the organisation for over 20 years and have pioneered the use of phase change materials and low energy ventilation solutions. Monodraft are very pleased to be sponsoring this award, as we recognise the importance that building simulation has in delivering a low carbon and sustainable future. Monodraft are a British green tech manufacturer, and we pride ourselves on innovation. Within the award, the finalists have all shown creative solutions within an engineering context. To reach the UK's commitments for a low-carbon society, it will require very creative and forward-thinking mindsets to reach the goals that society requires. Conventional building solutions that are now considered mainstream will become obsolete in a low carbon future. Being able to determine design and real-world performance data will become a necessity to ensure that new innovative designs are taken forward in a risk-averse and conservative industry such as construction. With regard to how as a company we are looking forward, 18 months ago we fundamentally changed our company design perspective. As a manufacturer of products, it is very easy to become compartmentalized in how much energy your products use. We now focus on a holistic building's energy and carbon use rather than of the products we manufacture. I'm pleased to say that 18 months later from this rather lofty ambition, we are due to launch our first product that provides a zero carbon ventilation solution. So once again, well done to all of the finalists and congratulations to the winners.
So I'll give it back to you, Darren.
Okay, thank you, Alex. Can I invite all our sponsors to reveal themselves, unmute and start their videos. So we're running a little bit behind. I was hoping to have about 15 minutes. Perhaps we'll just take 10 minutes to have a short debate. I'm still missing two. We should be having Nick Hopper from Monodraft, Andrew Hilmy from EDSL, Nagman Khan from SimScale, Eric Roberts from IES, and David Cocking from Design Builder. So I'll start off with a question. When I was a bright-eyed graduate engineer 25 years ago, I had dreams of all singing, all dancing, validated, multi-physics, building simulation tools applied interactively in real time, driving truly holistic building design. We're now in the fourth industrial revolution, and some specialist disciplines may still be separated, working in silos, reinventing the wheel. So my question goes beyond integration versus interoperability of tools. How do you see building simulation bridging this divide and delivering the true value that it has the potential to deliver? Who would like to respond? Long question.
Do you want me to go, Darren?
Okay, Dave, far away.
Okay, thanks. Actually, quite a difficult question to answer in a really short time scale. So I'm going to start by just taking a look at only a few aspects of current mainstream modelling and comparing that to what I would have seen as the situation 25 years ago. So 25 years ago, there were actually very few modelers, most of them using text-based tools. Graphical interfaces have massively improved modelling productivity. You can now calculate solar gains and cooling loads in minutes. 25 years ago, it probably took you days. You can now readily run full year climate-based daylighting simulations. Life cycle analysis will just been a pipe dream then, but it's available in the tools today. You can now feed in BMS data to calibrate existing building models, even write your own scripts to incorporate manufacturer's control logic. Cloud computing, been mentioned a lot today, it's made a massive difference. And you can now do truly holistic design that's viable for industry. And that's only been available in recent years via tools like multi-criteria design optimization. You can also demonstrate compliance with numerous building certification rating schemes, and they weren't around 25 years ago. That's made a massive difference fighting climate change. I could go on, but I guess my overall point is that it's really a positive picture, I think, for our industry. Software is now able to do the kind of things you dreamt about 25 years ago, plus a whole lot more that probably wouldn't have even been on your radar. We've still got a lot to do, of course. Our approach at Design Builder is to incorporate the world's best simulation engines in a fully integrated interface so that your energy, comfort, heating, cooling loads, daylight and CFD simulations can all inform each other within the interface in a very holistic and optimized way to produce optimal designs. That covers most of industry's needs, but it won't work for all firms. Many firms will still want and need to use multiple tools, perhaps to include applications like acoustics mentioned earlier. In my opinion, given the massive array of complex issues that our industry needs to deal with, the missing piece really is interoperability. We need to find better ways for tools to work seamlessly together without wasting time rebuilding models in each software. We're continuing to do that, as I'm sure others are.
I'd like to invite one of the other.
Can I go next? Hi, Darren, and yeah, thank you to all the other panelists as well. Really interesting presentations. I think I agree with bits of what David has said as well. I think from SimScale's perspective, look, what are we doing here? We're talking about building physics, right? So we want to capture a lot more of the physics. And 25, 30 plus years ago, as I mentioned in my presentation, we didn't have the computational power to be able to do that, to model everything explicitly. So we used a lot of simplifying assumptions, which was great, and it's been working great for now. But now we want to model more things, bigger things, faster, cheaper. So these are the trends that the market is pushing on the software development companies. So we saw some really great innovations coming up from the companies. SimScale is also working on on similar things. I think scale is very important. Speed is very important. A lot of the other vendors talked about optimization, right? This is very important. And optimization can only happen when you have a large number of subject simulations, right? It might be dozens, hundreds, if not thousands. That needs speed. It needs computational power somehow, right? So cloud, obviously, fully accessing the cloud is really important as well. I don't think you really need one tool to rule them all, as they say. I think it's okay to use specialist tools and link them together in a really easy to use and understand workflow. And opening up the tools is really important. So I think most, if not everyone, has some kind of API available now, publicly available API, where users can upgrade their skills, code something up, a bit of scripting, and they can talk to different software and make the different software talk to each other. And I think going in that direction is really important. And if you look at skills as well, the graduates coming out, they're taught coding now in the university courses, in engineering courses, architecture courses. That wasn't done 25 years ago. So we're seeing a lot more skills, which is going to enable that interoperability as well in the near future.
Thank you. Would one of the other panelists like to have their thoughts? Go, yes, Andrew, please.
Yeah, thanks. Yeah, I think I completely agree with Nagman and David. I think that there's a lot of value in recognizing the skills in the individual tools that people are using in the industry currently. Quite a lot of these tools are quite tried and tested, and people have confidence in the results. And it can be a bit dangerous to try and create one tool which can do everything, especially if it's new and you haven't got trust in the data that it produces. And again, interoperability means that we don't have to have a big, heavy, bloated tool that's complicated to use. We make it more accessible to people, and as long as our APIs are very, very well designed, it means that we can still integrate these tools in a way that you can do most of your work in one tool and have a chain reaction with all the other tools to have the results simulated in the other tools and come back into one place. And again, I think there'll be a lot of importance on how we present that data to people. We can have web-based tools that make the data as accessible to as many people as possible. And that just makes it more accessible and gets more people involved, helps them understand, the data that they are getting, and encourages a bit more ambition.
Thank you. And Eric or Nick, have you got?
I think in terms of building design process, it's still a fairly linear process. In the same way, it hasn't changed in many decades from the concept all the way through the delivery. You'd have thought with the use of simulation and that coming in, there should be a lot more feedback loops within that design process to do that. And it's had a fairly limited effect. I think most people still think as simulation as doing a bit of building regs compliance. That's their kind of understanding and knowledge of it. In terms of, yeah, I agree. This, you know, there's been so many simulation tools developed over the decades. You know, I think last time I looked, there'd been like 200 different simulation engines developed, most of which have fallen by the wayside over the years. So there's been huge efforts within this over the years for where we've got to. Relatively minimal impact over time. You know, we've got the potential to bridge that gap between all the different disciplines and fill that and actually improve buildings. And with the advent of greater computing power and all the different things that we can actually do now, it's time for that really to be shown and brought through and improve that design process and move it away from this very linear timeline of delivery on projects that we have.
Thank you. And Nick, have you got something you'd like to add?
Yes, so as a manufacturer's perspective of products, what I have been really pleased with the building simulation developments over the years is the ability to actually graphically show the performance of buildings and the influence of different strategies. However, that impact on post-occupancy and the linking of the amount of data coming back out of buildings now, I think that's the next element that's going to go forward with building simulation.
Okay, yes. Have you got any other thoughts on this, or I'll move on to another question? Anyone? No? Okay, shorter question this time. As simulation engineers, we now need to have developed a vast array of different personal skill sets. So what advice would you give to simulation engineers trying to grapple with this challenge? What are your top tips? Anyone?
I think there's an awful lot of I think it may have been Nagman that mentioned it. We're seeing an awful lot of the guys that come out of universities now. They're actually being taught coding, and the impact and the difference that kind of mindset can make is enormous. It really opens up another dimension. So I think if there was one thing, I think for me it would be that, is to kind of try and take that kind of coding approach, maybe have a look at some of the scripting capabilities that are available, that again open up just a whole new world of modeling.
Okay.
I think that's a good point, Dave, but as long as you've got the technical skills taught to you as well to back up that coding and to enact what you're looking to code properly.
Yeah.
I mean, there are quite a lot of online courses available now. There's more than ever, really, because there's so much emphasis on learning to program being so useful for so many different industries. So having a look at some of these really good online resources as well is definitely a great place to start. And then once you've got the basic, because the principles behind one programming language is so applicable to all of them, really. So once you've got a little bit of experience with one, you can then start to look at the APIs that are available in tools that you might be using, and just even find small ways that you can speed up a repetitive task that you're doing. Any small repetitive task, you can just sort of always be thinking about what you can do to make it more efficient with this new tool that you've got available to you. I think that's really valuable. I mean, that's something I did when I was in consultancy in EDSL, and now I'm a software developer there. And that was something that I did while I was using the software as a user. I was always thinking, how can I make this quicker? How can I make this more efficient? How can I get more results in the same time period? And that's just so valuable.
Thank you. I hear the judges are ready to go to the award ceremony. So unless there's a very quick top tip that anyone wishes to add, is that a no?
I would just like to add that the ability for building simulation engineers to pull the data out of the computer model and actually present the information, but also to go further and investigate the results they're actually seeing rather than accepting it at face value is a really important aspect.
Darren, final point. I think generally there's been a big explosion in data science skills across the board, across all industries. So you know, understanding large amounts of data and how to interpret that is a great skill to have these days.
Fantastic. Thank you very much for your contribution. I'd like to invite Darren Coppins back for the hosting the award ceremony. Thanks.
Thank you, Darren. One of the disadvantages of being a judge, and this is the third or maybe fourth year that I've been a judge for this event, is that you actually miss the presentations and the panel debate. So I look forward to watching that back on the video when it's available. I believe we have the Young Modeler Awards now, do we, Alex? And then we move on to the main awards after that.
Yes, that's correct. Yeah. So. Yeah, so this year we introduced a second award, which is the Young Modeler Award. We had many entries for the first time we're actually hosting this kind of event, and we are going to hear from Gabriella, the winner of the award.
My name is Gabriela Costa, and I'm a Senior Sustainability Consultant at Zyco UK. And I've been part of the Building Simulation Group Committee since 2016. And I'm delighted to announce the winner of the Building Simulation Young Modeler Award 2020. This is the first year of the Young Modeler category of our annual Building Simulation Awards. So I'd like to thank all young modelers who applied for it. We received a number of applications from across the globe, from academia, students, industry practitioners, and it's great to see remarkable work from all these sectors. Thank you all, and keep up with the good work. I'd like to mention that it was a tough decision to make on deciding who would win this award. And although we reached a conclusion, we felt that one participant deserves a high commendation. Our high commendation goes to Nishish Jain, a PhD researcher at the Institute of Environmental Design and Engineering at the University College of London. Nishish has outstanding work on knowledge transfer. He's also making building simulation accessible, developing tools with software companies, and has contributed to the development of CIBSE TM63. This technical memoranda talks about the building performance modeling and calibration for evaluation of energy in use. Well done, Nishish, for being such a role model in advancing building simulation practices. And now to the winner. The winner of the Building Simulation Young Modeler Awards 2020 is Wei-Jun Allen May from Cyclone Energy Group, based in Chicago, United States of America. Congratulations, Alan. The judges praised Alan's great presentation of a few examples from the 140 models he has worked over the past 4 years. But most importantly, his advocacy of performance-based compliance and modeling-supported design, and improving commercial software development. His work has also been featured in a case study by IES about Alan's modeling practice in the US, and recognized Cyclone and Alan's effort to advance modeling and deliver high quality and reliable analysis for their clients. Also, Alan's plan to promote building simulation in his career include helping students to be more exposed to real-world modeling practices in conjunction with universities and mentorship programs. He's also keen on standardizing modeling procedures and guidelines, and also working towards qualification for modelers. Publicly sharing of modeling work to the general public to raise an awareness of the building simulation industry is his last step on advocating building simulation. His engagement with industry bodies such as ASHRAE and CIBSE is extremely valuable and also shows that he's in the right path. And we at the Building Simulation Group Committee are pleased to welcome you in our committee next year. Please welcome Alan's acceptance speech. Thank you very much.
Hello, CIBSE. My name is Alan May. I work as a senior building analyst at Cyclone Energy Group, a Chicago-based building energy consulting firm. It is truly a great honor to receive the Young Modeler Award. I would like to thank CIBSE for setting up this award category to recognize young professionals in the building simulation community. I've been in the industry for 4.5 years. My employer, Cyclone, and my boss, Benjamin Skelton, have always been my biggest supporter. I had the opportunity to work with some of the best architects, engineers, and developers on many fascinating projects. I appreciate the support and the great teamwork. In the past several decades, building simulation has gradually become one of the most powerful tools to support and inform building design and operation. There are many software on the market today to meet our different needs. There are lots of standards, guidelines, and research papers to advanced modeling. It has supported the high performance movement, and I believe it will continue. And also it will advance low carbon, regenerative, and resilient buildings. I look forward to working with CIBSE, ASHRAE, CIBSE, and other organizations to advance modeling in the AEC industry. Lastly, thanks again for this great honor, and have a great day.
Over to you, Darren.
Thank you very much, Alex. Very well deserved award there. I'm just going to share my screen, and I'm going to now run through the judging that we have of the presentations we reviewed earlier. So I'm Darren Coppins, and again, I get the privilege of being chair of the judges, something that I've done for a number of years, and it's by no means an easy thing to do to judge the videos and the presenters on the quality of their contribution to our industry. Something that is actually very important at the moment is the climate crisis, and we cannot ignore what we need to be doing for it. An accurate modelling of buildings for real performance is an opportunity for our sector to rise to the challenge that the climate crisis presents. All the entries in this year's awards demonstrated the best in the industry, with 6 exceptional shortlisted entries setting the bar for the rest of our community to follow. I would just like to pass now to Gabriella to say a few words.
Thanks, Darren. It's been great to see so many good entries, and it's the shortlisted candidates, they did an amazing job at presenting their work, and especially I would praise all the visual representations that we've seen here today. But mostly, I think that what stood out for me was the potential that building simulation has now to become more integrative and looking into things more holistically. So moving away from an energy-based simulation engine to a more holistic comfort, health, and well-being tool. That's been very good to see in this year's entries. Now over to Vasiliki for her closing remarks.
Yeah, and a short comment from me, also highlighting what you've just said about the creativity and the innovation we've seen in all the entries, and how they use different tools to highlight the importance of this visual representation of building simulation results, and that provides effectively a common language for all designers. And this is very important to drive building design, which is what we hope we're doing. Yeah.
Okay, thank you, Vasiliki. So we have 2 runners-up, and Vasiliki, would you like to talk about the first runner-up?
First runner-up in order would be Shane Orme from WSP, and modeling the world's tallest tower. So congratulations. And I would particularly like to commend you on the representation of physics in this challenging environment, and the scale of the projects and the energy savings that you managed to do, but representing physics so accurately and in an innovative way.
So congratulations, Jay. Gabrielle, would you like to present our next runner-up?
Yes, now to the second runner-up, Adrien Dumoulard from France, on the innovative methods to minimize simulation and analysis time. I think I picked up a little bit of the end of the debate about the use of data and handling huge amounts of data. So well done for this new method, and I hope it becomes more replicable and people can integrate it at early design stages as well as later design stages. Well done.
Thank you, Gabriella. Now we get on to the winner, and I'm very pleased to say this year's winner is Meredith Davey with Jewel Shanghai Airport. And aspects of this entry, the judges felt, was a level of attention to detail, the methods used to understand the implications of the designed desires, such as the waterfall, and how that would impact thermal comfort, the way the trains were optimized in terms of the delivery of passengers right into the center, but thermal comfort was still important, as well as the visual representation that was produced to explain clearly in a very short amount of time what was actually happening in terms of the thermal comfort within the space. So well done, Meredith, and well done to our two runners-up. Again, fantastic entries, as was all of them today, and all of the entries that we've had over the period of these this competition. I would just like to hand back now to our chairman, Darren Wolf, to close this year's competition.
Thank you very much. And congratulations to all the entries and shortlisted. It's my job to close out the CIBSE Building Simulation Awards 2020. And I'd just like to say that these events don't happen without an enormous amount of effort in the background. So a big thank you goes out to our organising committee, all our reviewers within the two sets of awards, the judges, you just did a fantastic job in a very, very short period. Thank you for that. Our social secretary, our sponsors, and CIBSE for supporting this event. A special thank you goes out to Alex, our event secretary. He's been busy behind the scenes driving the event today, but spent a huge amount of time coordinating the event over the last few months. So thank you for that. Finally, congratulations again to all the winners and shortlisted entries for their inventiveness and passion for building simulation. That's evident to all. We now have a great format for the Building Simulation Awards, including the Young Modelers Awards. So I hope all of you that could enter next year do think about doing so. I'd now like to close these awards and hand over to Managing Director of CIBSE, Rowan Crowley, for his closing remarks on Build to Perform.
Thank you very much, Darren, and congratulations to the BSG on this year's awards and the impressive range of entries. Good afternoon, everyone. Build to Perform is CIBSE's Showcase Live event. So this online event is not actually what we planned at the start of the year. And it's the first time that it's been delivered online. But it has allowed us to meet with and provide the CIBSE community with a place and way to access the programme sessions and information once again. And all this whilst avoiding the usual problems of travel and the weather. This year's programme focused on the priority themes identified by CIBSE's Knowledge Management Committee and Knowledge Generation Panel. To remind you, these are net zero carbon, health, well-being and safety, climate adaptation, retrofit and refurbishment, circular economy, digital engineering, and smart buildings. You'll have seen all of them in the programme this year. Alongside these themes, there were also discussions on topical issues such as new policy directions, competency and skills demands, and the challenges posed by COVID-19 and Brexit very shortly. We are mindful that many of you will not have been able to attend all the sessions of Build to Perform and will want to catch up or revisit them. We have therefore organised Purchase on Demand event access, available from next Monday, 30th of November. To access the full Build to Perform programme on demand, you will need to purchase a full access ticket, which costs from just £20. This will grant you access to all the sessions recordings for a period of 3 months. A link to purchase this can be found on each of the session pages or on the Build to Perform website at cibse.org/B2P live. And now just a few thank yous. First up, our thanks go to our virtual exhibitors, without whose support this event would simply not have been possible. They are Fujitsu Air Conditioning, Kingspan, Lochinvar, Mitsubishi Electric, SWEP, Trimble, YGHP, and of course, CIBSE patrons. We thank them all for their support and presentations, which greatly added to the Build to Perform programme. Major thanks also go to all our presenters and session chairs. The high quality of the programme and the appreciation that has resulted is entirely due to their knowledge and skills in delivering it, and it is greatly appreciated across the sector. As Darren indicated earlier, events like these, and Build to Perform in particular here, require a large number of people to pull all the elements of the event together. And this starts with CIBSE's technical team, Hywell Davis, Anastasia Milona, and Julie Godfroy, who worked incredibly hard and with very short deadlines to pull together the programme and secure the presenters. Coordination and delivery of the programme, as well as a vast amount of work in the lead up, was handled by Lucy Bamber, Pom Daniels, and Jenny Porter, the last named from StepX, our partners in organising Build to Perform. I think many of our speakers will remember and recognise their voices from the support and guidance they all provided. Finally, we thank all our delegates for logging on and joining us at Build to Perform this year. Build to Perform will return next year on the 1st and 2nd of December, although we're not quite sure of what format yet, and we'll be keeping people advised. The Build to Perform team wishes you all a safe, healthy and relaxing Christmas, a speedy return to the new normal in the new year, whatever that proves to be, and we look forward to welcoming you all back at Build to Perform in 2021. Thank you all very much and see you next year.